Hi everyone, in this video we're going to talk about trigonometric derivatives. But before we get to the derivative of trig functions, we want to talk about this limit. Earlier in our class, we talked about the limit as x goes to 0 of sine x over x. And we did, back when we did the section on the squeeze theorem, we were able to, if you can go back and look at that video also, the squeeze theorem allowed us to say that the limit as x goes to 0, and we had the negative absolute value of x over x is less than sine x over x, which is less than or equal to the absolute value of x over x. So this is back from a few videos ago. And as x goes to 0, this went to 1, and this is sine x over x, and then this also went to 1. And so by the squeeze theorem, then we can conclude that the limit as x goes to 0 of sine x over x is equal to 1. And so this, we're going to use this in order to come up with a derivative for our trig functions, mainly sine and cosine. The other limit, there is a geometric proof for this. And I will record a video for those of you who want to see the geometric proof for it. And it's pretty interesting. It involves the triangle inside a unit circle. And so I will create that video. Separate video, not proof. And that video is just, it will be optional for you to watch. It's a really fun proof to do. And it also reviews a lot of the trig that you may have forgotten. So it might be nice to just kind of watch it, but know that you won't be responsible for it. It's just more of an enrichment type of concept when I record the geometric proof for why the limit as x goes to 0 of sine x over x is equal to 1. And I should have really used my limit notation here. The limit as x goes to 0 is between 1 and 1, so it must be 1. Now for the second limit, the limit as x goes to 0, 1 minus cosine x over x. This we can use a trig identity in order to prove it, now that we know this limit is 1. And but this limit, the limit as x goes to 0, 1 minus cosine x over x is equal to 0. And I'll include the proof of this one when I do the separate video for the geometric proof of sine x over x, so that you can see why this one is also equal to 0. So now with these limits, so the limit as x goes to 0 of sine x over x, what that allows us to do is essentially that for any angle, so if I have theta goes to 0 of sine theta over theta, this limit is going to be 1. And so I can just change the variables. So if I have the limit as t goes to 0 of sine of t over t, then this is going to also be 1. So you kind of get what I'm saying. Essentially, if the argument, right, this is the argument of your trig function, matches the denominator, then the limit is going to be 1. And so for our first example, we have find this following limits. The limit as x goes to 0 of sine of 5x over 5x. And so as I was saying here, if the argument of your trig function, so in this case, this is called, right, the argument is whatever is inside the function. So the argument matches the denominator, then the limit is going to be 1. And so for this one, the limit as x goes to 0 of sine of 5x over 5x. So notice that I could really easily let theta be 5x. And so then this becomes the limit as theta goes to 0, because if x goes to 0, then theta also goes to 0, of sine of theta over theta. And so this will be 1 based on the work above. So I don't have to make that substitution. As soon as I see that the argument matches the denominator, this limit I can just say is going to be 1. So what about this one? The limit as x goes to 0 of sine of 3x over 6x. So does the argument, the 3x, does it match the denominator? No, right? So the 3x, the argument is not equal to 6x. Darn it. But can we make them equal? Yeah, I can rewrite it I can say the limit as x goes to 0 of sine of 3x over 6 is really 2 times 3. So I can say this is 2 times 3x. Right, and now properties of limits allow me to bring that 1/2. I can say this is 1/2 times sine of 3x over 3x. The times. So 1 times sine 3x, 2 times 3x will give me my original 6x, but this allows me to, so the property of limits that I'm actually using is bringing the 1/2 out. So this is the limit as x goes to 0 of sine of 3x over 3x. Now the argument, right, the thing inside my trig function, my sine, matches the denominator. So this is going to be 2 times 1. So that limit is 1 and not 2, 1/2 times 1. So this is equal to 1/2 times this limit is 1. And so I just get 1/2. So that is our limit. So we can manipulate our expression so that whatever the argument inside the sine is, I can try to make the denominator match that. So let's try a couple more examples. Part C of this example 1, I have the limit as x goes to 0 of sine of 8x over 8. Now this is a little bit different because here I had sine 3x and 6x, so I could manipulate the 6 and say that's 2 times 3x, and then I have my argument matching the denominator. But here I don't really have any coefficient to work with. So, but one of the things we can do is like, well, I would like this, I want the denominator to be 8x. So how can I do that? I already have the x, I just need the 8. So multiply top and bottom by 8. So what I mean by that is I'm going to have the limit as x goes to 0 of sine of 8x over x. And we're going to multiply top and bottom by 8. Right, 8 over 8. Notice that this is a funny looking one. 8 divided by 8 is equal to 1, so I'm not changing the value of the quantity sine 8x over x because I'm multiplying it by 1. But what this allows me to do is I can say this is the limit as x goes to 0 of 8 times sine 8x over 8 times x is 8x. And now I have my limit as x goes to 0 of sine of 8x over 8x. Now that's going to be equal to 1. So I'm going to have 8 times the limit as x goes to 0 of sine of 8x over 8x. And that would then be 8 times 1 because this limit is equal to 1. So the whole limit is 8. Now our next example is a little more complicated. I have the limit as x goes to 0 of tangent of 20x over sine of 8x. So that looks a little different than just sine 8x over x. So, and also now my sine is on the bottom, but that's okay. So if, let me go on a side note here. If I had the limit as x goes to 0 of 8x over sine of 8x, will that still be 1? Yes, right, because that's just the reciprocal of this one. So this is my lazy because 8x over sine of 8x is really 1 over, is just a reciprocal. And so this limit as x goes to 0, this limit will be 1. So you're still going to get 1. So that will still work. Now, with this, let's try to figure out what to do because I have tangent and I have sine. So one of the things I'm going to try to do is break up the tangent. I know, what do you know about tangent? So let me write this way. So tangent of 20x times 1 over sine of 8x. I'm going to try to separate the trig functions. And so this is like over 1, right? I guess I don't need to do that. And then what is tangent? I know that tangent is sine over cosine. So this will be sine of 20x over cosine of 20x times, and I still have my 1 over sine of 8x. So what am I trying to do? I'm trying to build something that has the sine 8x and the 8x on top, so I'm going to need an 8x over here. So I'm trying to separate, but now I have sine of 20x. So I don't want that cosine 20x on the bottom, I just want 20x there. So I'm going to keep going and splitting these things up. So I want the trig functions to be essentially by themselves. So I'm going to have sine of 20x. So I'm going to split up the sine of 20x over cosine. It's going to be times 1 over cosine of 20x. Do you agree that these are the same? Right, numerator times numerator. There's an invisible 1 here. Denominator times denominator. Times, I still have my 1 over sine of 8x. So now I'm getting somewhere. So now, what do we want? We want 20x there, and we want 8x here. So we have a little more work to do. So let's see. How about we multiply top and bottom by x? So what I'm saying is multiply top and bottom by x, and so when we multiply that, I'm going to have the limit as x goes to 0 of, I'm going to leave that as sine of 20x times 1 over cosine of 20x times, now I have x over x, right? Again, this is equal to 1. So, but I'm going to take this x and put it on top of this one. So it's going to be x over sine of 8x. And then this bottom x, I'm going to multiply it by the 1 that's over here. So I'm going to have sine of 20x over x. So what I did is I have my x over x, which is 1. I'm just redistributing this, not distributing, that's not the right word, like rearranging them so that they work for me. It's like a little puzzle, right? I want 8x over sine 8x here. So I'm multiplying first by x over x, and I'm going to put, I need the numerator x. I don't want it in front of any of these. I want it right on top of the sine of 8x. So I'm going to take that x and multiply it by that 1. I'm going to take that bottom x and multiply it by this one, right? I still have 8. X divided by x is still 1. Now I need to get 20 here and 8 there. So multiply by 20 over 20 and multiply by 8 over 8. That's a times. So we're almost there. So this will be the limit as x goes to 0 of 20 sine of 20x over 20x times 1 over, we're not doing anything to this. And now multiplication, right, is just, I just multiply everything here. So it's not like addition, so I don't have to say 8 times x, 8 times 1, and 8 times sine of 20x, right? This is not addition, this is multiplication. If you have 2 times 4 times 3, right, you don't say 3 times 2 and 3 times 4, you just say, oh, this is just 2 times 4 times 3. So you will say 8 times 3. So you can either multiply it, right, what is this? The associative property of multiplication that allows you to move the factors around and still get the same product. So that's what's happening here. So this is all multiplication. So the associative property of multiplication is what's allowing me to be able to arrange these terms how I want them to be. If I had addition or subtraction in here, then yes, I will have to distribute to each term, but these aren't terms, right? Terms are separated by a plus or a minus. These are multiplications. So where were we? So 20 sine of 20x over 20x. That one stays the same, and now this one becomes 8x sine of 8x. And so now I can take this limit. As x goes to 0, this limit is going to be 1, and this limit is also going to be 1. So I'm left with, as we plug in 0, this is 20 times 1 times 1 over cosine of 20 times 0, which is 0, times 1. And this is, wait, what happened to my other 8? I should still have 8 over here, because I have 8 over 8. So 8x and 8 times sine of 8x. So I still have my other 8 here. So this will be 1 over 8. And cosine of 0 is 1. So I'll just have 20 times 1 times 1/8. So it's 20 over 8. Reduce it so that it's in lowest terms. So 4 goes into both of those. So 5/2. So the limit is 5/2. And you can just leave it as a reduced fraction. No need to turn it into a decimal. Okay, so just to recap what we did in this one, we have tangent and we have sine. So the only thing that we know is that the limit of sine x over x is 1, or its reciprocal is 1. So we're trying to build the sine x over x or x over sine x so that we can say that that limit is 1 as x approaches 0. So I split up the tangent 20x and the sine 8x on the bottom as 1 over sine x, and then from there, right, tangent sine over cosine, then split this up also the same way that we did the tangent over sine as sine of 20x times 1 over cosine, and then just carry along that 1 over sine x. And from here we can start building. I know that I want this to be sine of 20x over 20x, and I want this one to be 8x over sine of 8x. And so we start building from there. Multiply by x over x, because that equals 1. Rearrange your x's where you need them. And then multiply by 20 over 20, that's equal to 1. Multiply by 8 over 8, that's equal to 1. So we're not changing the value of the original quantity. And then as we multiply those, we end up getting our limits, right? The limit as x goes to 0 of sine 20x over 20x. Now the argument is matching the denominator, so that limit is 1. The limit as x goes to 0 of 8x over sine of 8x, the argument matches what's on the other side, in this case in the numerator. So that limit is going to be 1, leaving us with 1/8. And then just multiply it all together and reduce. So let's try the next example. The limit as x goes to 2. So this is different because it's not going to 0. But notice what happens when you plug in 2. When you plug in 2, you're going to have the top is sine of 0, which is 0, over 4 plus 2, which is 6 minus 6. So you have that 0 over 0. So that is kind of like we know that the limit as x goes to 0 of sine x over x, right? This is 0 over 0 as well. It has that form, and this limit is 1. So so this is still going to that form, 0 over 0. So I want my argument to show up on the denominator. So let's see if factoring the bottom helps us get there. So I'm going to have sine of x minus 2, and you want to factor. So what two numbers multiply to negative 6 and add up to 1? That would be x, what's that, plus 3 and x minus 2. So there it is. I have my sine x minus 2 over x minus 2. So this, as x goes to 2, that limit is going to be 1. So this then is going to be the limit as x goes to 2 of just 1 over x plus 3, because this limit is 1 in the numerator. So as x goes to 2, we're going to get 1/5. Pretty cool, huh? And last but not least, this one. In this one, I don't have sines, so I have cosines. And be careful not to want to switch that cosine square with an identity. So here I see this more as a quadratic, but if you have 2 minus t squared, what would you do? You would try to factor, right? What does it factor into? It will be, what could it factor into? Let's see. It will be 2 minus t and 1 plus t. No, this one is plus and the other one is minus to make the signs work. And again, be careful not to reverse the order, right? This 2 minus t squared is not the same as saying t squared minus t minus 2. Don't just reverse the order because you want it to look nicer. This needs to be a minus t squared. So when I multiply, right, t times minus t, I get a negative t squared. So be careful not to say this is equal to t minus 1 because that's not true. But this is cosine. So that means I can rewrite this as the limit as x goes to 0 of, let me use the same factoring. So this is going to be 2 plus, instead of t is really cosine x. 2 plus cosine x and 1 minus cosine x all over x. And so let's double check it. 2 times 1 is 2. 2 minus cosine x. So 2 times are negative. So it's negative 2 cosine x plus cosine x. So that will give me negative 2 plus 1 is negative 1. And then cosine x and negative cosine x is negative cosine squared. So that is the correct factorization. And now I can use the fact that my limit as x goes to 0 of 1 minus x over x, this limit is 0. So I'll be left with the limit as x goes to 0 of 2 plus cosine x times 0. So it doesn't even matter what this is because when you multiply it by 0, you're going to get 0. And so I know I only did one example with this one, but it essentially works the same way. We want to be able to match the argument of the cosine with the x, with the denominator. And the limit as x goes to 0, so I'm going to do a quick example, make one up here. If I have the limit as x goes to 0 of, say, 1 minus cosine of 7x, I will need to have a 7x on the bottom for this to be 0. If I didn't have a 7x, I will do the same thing that we did above with the sign, right? Multiply top and bottom by 7 so that I get the same argument in the denominator, and then that limit is 0. So the two limits that are important here are that the limit as x goes to 0 of sine x over x, that's equal to 1, and the limit as x goes to 0 of 1 minus cosine x over x is equal to 0. So those are the two big limits. In the next video, I'm going to record how to find the derivative from the definition of the derivative of sine x, and then use that to find tangent and all the other ones, and we'll have some fun with product rule and quotient rule using trig functions.